In this explanation we're going to look at some differentiating rules and especially focus a bit on the chain rule. And let's first look at some of the rules we discussed already in differentiating. Especially the power rule is something that we looked at already. And basically that was saying if you start with a function x to the power n, then the derivative can be found by taking n times x to the power n minus 1. So this can be used in various situations. If I, for example, have something like 5x to the power 3 minus 4x squared plus 6x plus 3, the derivative can be found by taking 5 times 3x squared, so that will be 15x squared, and then minus 4 times 2x, because 2x to the power 1, so that's minus 8x, and then the derivative of 6x is just a constant, plus 6 and the 3 cancels out because the derivative of a constant is 0. We saw that also this power rule can be applied if the n is a negative number or a fraction. So for example, if you have something like gx is 1 over x to the power 3, then you can always write it as x to the power minus 3, therefore the derivative will be minus 3 times x to the power minus 4, because minus 3 minus 1 is minus 4, so you can write it as minus 3 over x to the power 4. Yes? Okay, before we move on to the chain rule, I would like to look at some special situations that we already can solve. So I would like you to look at these two examples. If I have something like 3x plus 1 times 2x minus 5, and we would like to find the derivative. Maybe it's a good idea to just try this yourself first and see what you find as the derivative. And then now I'll give the solution. So in a situation like this you always need to expand the brackets first, if that's possible at least. So in this case, if you expand the bracket you have 6x squared minus 15x plus 2x, so minus 13x, and then plus 1 minus 5, it's minus 5. And now you can easily write down the derivative 12x minus 13. And so it's important that you expand the brackets first. Second example, it's something that we can do already if you have some good algebra skills. Suppose I look at something like x squared minus 5x divided by root x. And this looks quite complicated, but it turns out by applying some algebra rules we can already find the derivative here. And again, I would like to give it some thought yourself first. The method that solves this problem is by realizing that if you divide by root x, so by one term, it can be split into separate fractions. So you can write it as x squared over root x minus 5x over root x. And notice that this can be simplified. X to the power 2 divided by x to the power half, so that will be x to the power 3 over 2, or 1.5. And x divided by root x, it's x to the power half, so minus 5 x to the power 1 over 2. Well, now, although it may look a bit complicated, it's actually the power rule can be applied. So if you write out the derivative here, x to the power 3 over 2, so the exponent we put in front, so 3 over 2, and then x to the power half, because 3 over 2 minus 1, so we have 3 over 2 x to the power half, and here we have 5 times half, so 5 over 2 x to the power minus half. Well, that's already quite something. If you're this far, you can go one step further by turning into roots again. So we have 3 over 2 root x minus 5 over 2 root x. Because x equals minus half, it's 1 over root x. Okay, so this is all based on applying the power rule and using some algebra skills. Now we're turning to a kind of functions that we need some extra rules. And so we move on to the chain rule. In order to fully understand it, I think it's important that we refresh our memory about composite functions. So composite functions is something we discussed before. So I'd like to look also at an example there. Let's say we have fx is 1 over x and gx is 3x plus 5. It is possible to combine these two functions by filling in one formula in the other one. So for example, we can ask for the f of gx, which can be written like this. Probably you know the answer already. So we fill in the 3x plus 5 for the x in that formula. So it will be 1 over 3x plus 5. That's an example of a composite function. You get a different answer, by the way, if you do the opposite. If you take the g of fx, so then we fill in this formula in that one. So we have 3, so the x is replaced by 1 over x, 3 times 1 over x plus 5, so 3 over x plus 5. So that's how we learn to deal with composite functions. This idea is very useful because sometimes you will start with a function that's quite complicated and you can decompose it into two parts, so you get two functions that are a bit easier to handle. So let's look at an example. Okay, so decomposing functions, you could say. Let's look at something like y is 2x plus 1 to the power of 3. Although this is not extremely complicated. But this is a nice example where we can use like a decomposition. So that means we are looking for two functions, f and g, so that we can write it as the f of gx. Well, it's not really difficult to see. If you take fx to be x to the power 3 and gx is 2x plus 1, you can see that it perfectly works. If you fill in 2x plus 1 in that formula, you get the y. Okay, for the purpose of the chain rule, I would like to show a slightly alternative notation. So it's the same decomposition, but you can also write, okay, I call this part in the brackets, I call u, it's 2x plus 1, and then I write y is u to the power 3, and then the combination of the two, of course it means y is 2x plus 1 to the power 3. Yes? So it's quite useful for the chain rule that we can decompose it in this way. Okay, let's do one more example. Let's say we have y is root 4 minus x squared. And we like to do a decomposition. Then we can say, well, I can call the part under the root, that will be my u, so we can write down the u is 4 minus x squared, and then the y will be root of u. By the way, this is a 4 and that's a u. I hope you can see the difference. Okay, so this is about decomposing functions. That's something that we will need for the chain. Okay, let's move on to the chain rule. And to start with, we go back to this example. Suppose we're interested in finding the derivative of 2x plus 1 to the power 3. Well, you may say, well, if I see something like this, and what we said before, maybe it's necessary to expand the brackets and then do the derivative after that. And I think that's a very good idea, because although it's a bit of work, because we're dealing with the power of 3, think of the binomial theorem, it can be done, so we can expand the brackets and find the derivative. So actually I think it's a good idea to start with that method, because that's something that we know already. So let's expand the brackets. It's a bit of work, but the first term will be 2x to the power 3, so that's 8x to the power 3 if you expand the brackets. And then we have 3 times, well, 2x to the power 2 times 1, 3 times 2x, and then 1 to the power 2, plus 1 to the power 3. So we end up with 8x to the power 3 plus 3 times 4, 12x squared plus 6x plus 1. And then we can take the derivative there. So we have 24x to the power 2 plus 24x plus 6. And the 1 cancels out. So this is actually the derivative. But you can imagine that is going to be a lot of work, especially if we have something like 2x plus 1 to the power 10. So the good news there is like a faster method. And to illustrate it, we go back to this example. And before I write down the chain rule, I would like to do a little investigation. So we're looking for derivative. Well, you say, well, this is something to the power 3. Isn't it possible to just apply the power rule and let's try and say, well, maybe derivative, we could just say it's 3 times 2x plus 1 to the power 2, because that is what you would do for the power rule. And it turns out that this almost works. So let's see whether it's close to the real solution, because this is, we know that this is the real solution. So if you look at this one, it's equal to, expanded brackets, 4x squared plus 4x plus 1. So it's equal to 12x squared plus 12x plus 3. So here we have 12x squared plus 12x plus 3. And the correct answer is 24x squared plus 24x plus 6. So if you give it a good look, it's almost the same, only a factor 2 is missing. And so now we're actually almost ready to write down the chain rule. Notice that if you look at the derivative of this part in brackets, 2x plus 1, it's exactly 2. So now I would like to write down the chain rule, and it uses this idea of decomposing the function first. So remember that decomposing, we would write the y is u to the power 3, and the u is 2x plus 1. And now I write down the chain rule, which is something that we're not going to prove, but we just illustrate that it works using these examples. According to the chain rule, the dy dx, so that's the derivative, equals dy du times du dx. So it uses a u. By the way, this is a rule that is relatively easy to remember because, well, although we talk about derivatives, you cannot really say that it's like a fraction, but it looks, if it would be a fraction, you could say, oh, we'll cancel out the du and we just have dy over dx. So it's something that looks very logical. Now let's see how this works out. So we have y is u to the power 3. So we can write the derivative. So now not x is the variable, but u. Therefore, if you write the derivative as dy du. So the first step, dy du, it's 3u squared. Does that make sense? 3u to the power 2. And du dx is 2. Well, according to the chain rule, that dy dx can be written as 3u squared times 2. So you may even say 6u squared. However, of course, the u was just like a temporary variable. So our final answer we would like to have in terms of x. Since u is 2x plus 1, you can say it's 6 times 2x plus 1 squared. And that's the correct answer, because it's the same as this 24x squared plus 24x plus 6. Okay, so this is a powerful rule, but many times it's a bit strange in the beginning. So let's do one more example, and then hopefully you feel a bit more comfortable. Let's say we are looking at y is root 4 minus x squared. I think we already did a decomposition. So it's an example of a composite function. So if you write the y is a root u and the u is 4 minus x squared, then if you combine it, you have the function on top. Okay, now it turns out that these functions separate are relatively easy to differentiate. So derivative of root u, it's 1 over 2 root u. And we learned somewhere if you start with root x, then the derivative will be 1 over 2 root x. So now it will be 1 over 2 root u. So we can first write dy du, it's 1 over 2 root u, and derivative of 4 minus x squared, that's the du dx, it's minus 2 x. Okay, well now let's look at the chain rule. According to the chain rule, the derivative of this whole expression is dy du times du dx. So it's 1 over 2 root u times minus 2x. And again, we don't leave the u there in the answer. By the way, maybe we can first write this as one fraction, so it's minus 2x over 2 root u. Notice that we can cancel out the 2 there. So we are ending with minus x over root 4 minus x squared. And so here we are replacing the u by 4 minus x squared. So this method shows that now we are able, if you start with a composite function, and by the way, notice that this one we could then expand the brackets or use any other method we learned so far. So we were really depending on the chain rule here, and by following the steps, decomposing first and then take the derivative of each separate part, we were able to find the derivative.